Thank you, Rao. Thanks everyone for attending the talk. So first I want to acknowledge the research scientists who collaborated on this, on several material that I'm going to present today. This is the outline of the talk. For any research topic, I encourage my team to look at the data first, try to understand the data. Then once you understand the data, then come up with a strategy how to solve the problem that you are going to work on. So I'll give a very high-level overview of the data that we have at eBay for computer vision. And then talk about how we do visual search at eBay. As you know, visual search is a backbone for computer vision applications in commerce. What it helps is obviously, take a picture of something and then find it. You can also use the same backend, like visual search, to do other things. For example, go from an existing item in the inventory. Let's say if you're on the eBay site, you click on an item and find similar items to that. You can also train recommendation systems using similar architecture used for visual search. So I'm going to talk more on that. Aspect prediction are things like predicting brand, color, style, and so on, so that you go more towards product match or fine-grained search. Then take a deep dive into what does the neural network see when it looks at pictures, and the application we are going to look at is when the neural network tries to predict brand, what does it see? And we'll have some insights on that. So essentially going broad on the data and then look at a specific application, visual search, which could be seen as in a coarse sense. And then aspect prediction going a little bit deeper and narrower. And then specifically brand, when we train a system, neural network to predict brand, what does it actually see? It's more like making AI explainable. Okay, let's look at the data. Just to look at the volume of the data that we have and different diversity, about 59% of the listing is international, or also transactionals are in the same ballpark. And there are lots of buyers and sellers too. So which means, let's say you're looking at Air Jordan shoe, a specific colorway and specific model. There are so many sellers trying to list their own instance of the same product. So that way we have a diversity of image quality. This one shows the kind of traffic we get from US and UK. The thing I would like you to pay attention to is you can see there are different kinds of inventory for different site. Let's say watch in the US, camping and hiking and so on. UK, there are more brand related things. So depending on the inventory and the traffic, you may want to optimize your models to bias towards certain categories, right? So that your revenue is increasing. So that's the thing I'm trying to show here. Or maybe you want to have a specialized experience just for, let's say, sports trading card, right? These are avid collectors. So even though it may not be in the number one traffic, maybe you want to create a special experience for them. So that's the way we look at the data at eBay. Look at the traffic, which one is prioritize different categories. So at eBay, just like other e-commerce companies, we have item-specific information, things like title, image, and so on. I'll actually show a few more slides related to item-specific. We also have seller-specific information. We have seller ratings. We know how long the seller has been listing items, how experienced they are, what kind of categories they are experts in. Same for buyer. Maybe they are very frequent buyer or not that frequent, and so on. Also session data. When somebody searches for a query, depending on the location or time, season, or other user characteristics, what kind of path do they take during the journey when they come to our site? Specifically, item-specific data, because that's what we currently use to train our visual search system. If you go to view eBay page, this is what we call view item page. When you're interested in a specific item, you go here. There are some things that you can notice here. There is an image. There is also a title. There is a price. There are other things on the right side. You can see like a seller information, like a rating and so on. And below, there are some recommendation related things. So what you look at, what I'm going to talk about more are things like this, just the image. And at the top, you can see the categories, because eBay has some kind of a hierarchy to associate every item, every listing item. And each listing may have multiple images. I just picked one with a single image here, but they can have multiple images. Also, if you scroll down, there are these things, what we call aspects or item specifics. These are things like brand, style, width, heel height, and so on. If you notice, not all of them can be predicted just from a single image. For example, it's hard to predict its US shoe size 6 just from a single image, RGB image. Right? So what we do is we pick only those aspects where you can actually train a visual, like computer vision system to predict these aspects. For example, brand, style, and so on. Right? There is also even more richer information description. We're not using this for the systems I'm going to talk about today. I'm just telling this is another data associated with the single item. So this is an example of category hierarchy. You can see all fashion-related things, most fashion-related things are under what we call clothing, shoes, and accessory. This is what we call level 1 category. And if you go to the bottom, you see that's what we call leaf categories. You may have things like athletic shoes, boots, and so on. Just for the US site, we have more than 16,000 leaf categories. And we actually use these labels to train our system. For example, we may have let's say 10,000 images of boots with stratified sampling, right? And maybe 10,000 images of heels and so on. And now we can train a neural network to predict, given an image, predict boots or heels or flats. So that's what we call category prediction, right? And we also have another system that actually predicts aspects. So as I mentioned earlier, these are things like, heel type, material, pattern, and so on. We pick only the visual aspects and train neural network for that. Now let's take a little bit more detailed view of the data. This is a visualization of handbags at eBay. You can see that almost half of the images on the left side, the background looks a little bit more complex. They're not. If, for example, let's say you're trying to remove the background, they may not be that easy to remove the background from these images, right? About 10% of the images on the top right, I circled it in blue. They have white background, perfect white background, and all others on the right side, they have relatively simple background. So you may be able to use something like GrabCut, to remove the background. This is just talking about the background, right? Here is another example. On the left side, you see all these Louis Vuitton bags with white background. And eBay, we also have images on the right side. This is actually a strength for us when we train our models. We have image qualities, like very good image quality and also poor image quality, because there are lots of sellers listing images with different quality. Also, here I'm showing an example where white background is considered high image quality, right? When you look at some categories like furnitures, right? In this case, outdoor furniture, this kind of background is probably better than having a white background, like showing the context there, right? However, if you have something like a dress, like the picture on the left side, you may want to have something like a white background or something on a mannequin. This kind of image is considered bad quality for dress. Right. Also, if you look at a single object, in this case shoe, the 3D object, there are so many different ways we can take the picture, right? In this case, the backgrounds are all kind of similar, I would say, but the information content of from the object itself is very different, right? So this also poses challenge to us. However, we have these kinds of images for different listings. So when the user takes the picture from different angle or different composition, we do relatively well. Okay, of course you can always break the system. I want to emphasize the sampling strategy. When we train our system, right, we have a long tail distribution. However you slice the data, let's say you slice by category, meaning the x-axis is category, and you look at the histogram, it will have a long tail. It's not a Gaussian distribution, it's a heavy tail distribution. Even if you slice by brand, or you slice by color, or slice by sellers, it always has this long tail property. This is actually a strength. We actually use this to samples, do stratified sampling, because you will always have a budget of, how many images you can have to train based on the GPU memory, or how many GPUs you have, or how long you have for training. So we always have an upper limit of how many images you want to have in your training set. And as I mentioned earlier, we have more than 16,000 leaf categories, right? So that kind of limits, how many images you can have per leaf category. If you look at the bottom region, so we actually stratify based on sellers. We don't want too many images from the same seller, because they may have this very unified way of taking the picture, right? We want diversity. We also want diversity in the product space, right? We also look at condition. There are lots of new and used items on eBay. Right, and also specific strong aspects like brand and model within specific fashion categories and so on. And also, let's say we are talking about shoes. We want to take shoes from different angle. We want to have representative images of shoes taken from different angles. So also, we remove duplicates, because if you have a budget of, let's say, 10,000 images per leaf category, we don't want to have duplicates or things that look very similar. So we pay careful attention to that. Now, let me show a high-level view of how we do visual search, right? So some of the things that we need to consider are, we have to come up with a simple system. There are memory constraints. Speed is also a big factor. And scalability and maintainability are important too. For example, you don't want to have like 100 different models. So, otherwise every time you train the models, you have to maintain 100 models. You have to maintain the life cycle of all these models. So those are other things that you need to consider too. So the architecture I'm going to show you now is pretty simple. Also, I'm going to show a simplified model. I think most of you are probably aware of deep neural networks. So you have different layers. Each layer lots of neurons. You feed the input, and then after you have several layers, you try to predict the output. So in this case, we train the neural network to have three different kinds of tasks. Okay, the first task here is the aspect prediction. For example, we feed lots of images from different brands, and then ask it to predict, let's say, Puma or Adidas and whatnot. The second one is leaf category prediction. As I mentioned, we have 16,000 plus leaf categories. We feed lots of images with different labels, like leaf category labels, and ask it to train. In fact, we start with leaf category prediction because we have very rich data for leaf categories. We train a system, neural network, to predict the leaf category, and then we freeze the bottom layers. Those are the common deep neural network. And we use these common layers to extract the information, and then we add more layers to predict things like aspects and so on. We are now working on joint optimization. It's pretty hard to do joint optimization and have very frequent model releases. So initial step, that's what we did. We trained a very strong leaf category classifier, and then we added new layers, in parallel layers, to predict aspects. We also use neural network to extract the signature, and we use a weak supervision in the sense that for the main model, we don't use Siamese or triplet embedding to extract the embedding. Embedding is like a signature that you're going to extract from each of the image. Because when you're doing visual search, you have to extract some signature from the input image, and then you might have extracted the signature for all the items in the inventory. Now the problem is, can we match these signatures? Which signatures look similar, right? Of course, your signature should be compact, and also this comparison, when you're comparing the signatures, that should be fast, right? So these are the considerations that we take. So in our case, we actually extract binary signatures. So we have a long vector of 4,096 binary values. These are ones and zeros, right? So it's like half a kilobyte of information per item. And when it's binary, when you're comparing two signatures, all you need to do is how many bits are different. This is the Hamming distance, right? And this is very fast to do. Like I mentioned, this is another view of seeing the same thing. You have some shared layers, and then you have three tasks. I'm showing only two tasks here: category prediction and signature extraction. When we extract the signature, we actually use a sigmoid layer. The sigmoid layer looks like S shape, right? It looks it has high values and low values. So the advantage of using sigmoid layer is once you train with the sigmoid layer to predict the leaf category, then you can extract the output from the sigmoid layer and then threshold with a value of 50%. Then you get ones and zeros. So that's a trick we use to get binary values. So I highly recommend, if you're trying out some system to just add a sigmoid layer and then train the system, then you can easily threshold it. Here I'm actually showing a view for 5 different classes from ImageNet, and this distribution, these clusters that you're seeing, they're based on the binary data, not floating point. Okay, so just using the binary signature, we are showing that in the neighborhood, meaning like a Euclidean, if two samples are neighbors in the Euclidean space, they seem like they are neighbors in the binary space. Here, I want to tell you something counterintuitive, right? When you're learning classification, let's say classification 101, you've probably been taught, it's good to have larger variance between separation between the clusters, right? That is good. So we want to have these different colors to be separated. The ability to separate different colors to different categories, right, is important. The second one that you probably taught is, given a cluster, let's say blue, the variance should be small, right? So we believe that for visual search, you need the spread within the class, but between the class, definitely you need separation. I'll tell you why. So let's say the blue dot, the cyan dot at the top is cluster is for shoes, right? If the variance is 0, then all of these points will be collapsed to a single point. When it's a single point, when you're doing visual search, you won't be able to tell different shoes apart, right? There are so many different kinds of shoes. So that's why we need separation within the cluster, right? Of course, we should be able to separate one cluster from the other cluster. That's also important, right? So that is something you may want to think about after you leave the room. Another thing you want to consider is when you're extracting this information, you have to extract so that you're using the information effectively. Let me give an example. Let's say you have a signature with 8 bits, right? The maximum amount of information you can store is 2 to the power 8, right? What does this mean? It means that you have like 2 to the power 8 buckets. And if you were to put your data in these 2 to the power 8 buckets, 256 buckets, are you going to have too many in one bucket and all the others are empty? Right? I mean, the ideal case, you should have like uniform, right? So here, what we are showing is for ImageNet, using the sigmoid approach. The ideal case is you have to be flat, right? 50%, right? But practically, you need some kind of redundancy because if some bit has noise, you want other bit to pick up that information. So what I've shown here is the 2 red lines. They are plus or minus 5% from 50%, right? And we actually have 84% of the bits that are within this range in our data set, which means that it's not bad. There is still some redundancy, so which means that we can actually reduce the 4096 bits to some other smaller value, let's say 2048, or maybe 3000, and still do well, right? So I encourage you to look at the occupancy of different bits in your data set when you extract the information. I want to recap because we went through a lot of things. I showed this architecture. I initially talked about the data, and then I talked about, when we extract the signature, what should be the properties of the signature, right? And it is another one. One of the properties is separation. The other property is, is it effectively capturing the information so that it's kind of, you're making use of all the bits effectively, right? So remember, I talked about different buckets, right? For example, at eBay, we have 16,000 plus leaf categories. In our case, each bucket is a leaf category, right? Well, let me step back a little bit. So in this case, when I say bucket, I'm talking in the category space. If you're talking about the binary vector, those buckets are a little bit different, okay? So what we do is, instead of searching the entire inventory, let's say 1 billion images, we predict the top categories, let's say top 5 categories, and we search only within those top 5 categories. So this way, instead of searching a billion, we now search only like tens of millions of images. So dramatically reduce the search space, right? It's a simple approach, but effectively reduces search space. Another advantage is, let's say you're uploading a picture of a shoe. We don't want to search in dress, right? If you don't do this, you may get your results from dress also. So in other words, when you do this top K, you get better precision also. For details, you can look at our KDD paper last year, visual search at eBay. You can see lots of details. And also when we say top K, let's say top 5, we don't blindly use top 5 all the time. So I show 3 examples here. C1, C2, C3, let's say these are the top categories. Let's look at the left side, right? I show the softmax score, which are like the probability score. It says it's 75% confident that it's C1, 10% confident that it's C2, 9% confident that it's C3, and so on. I'm going to use a threshold of 0.9, okay? So if I were to use top K blindly, I would pick even the category C5, which is 0.1% confidence, right? So which actually means that machine is not that confident about this class, but we're still using it for search. So that's not good. So that's why we use a cumulative score. In the third column, you see the cumulative score, which is actually the cumulative sum. So 0.7, 0.8, and so on. We go till we reach 0.9. Actually, my slide is a little bit wrong. It should be like a 0.91. It should be 4, right? In the second example, the one in the middle, the classifier is very confident, like 90% confident with the first class. So there's no reason to look at, second class or third class or fourth class or fifth class. So in this case, when we use cumulative score, we pick only the first class. So that way we search only the first one. We get higher precision because the neural network was not confident about the other classes, right? So I highly recommend to use something like this also when you're doing this fast narrowing down the buckets, right? So this way it's also dynamic. It's not hard-coded one. These are some more papers. I just took a screenshot from our paper. Essentially, you don't have to look at the details. I have in the legend. I highlight only 2 colors, which are the top 2 colors in the left side. The pink one is when you use cumulative, it shows that you get better precision than when you use blue. Blue is hard-coded 5. And then the bottom curves are using the traditional approaches like using k-means clustering. K-means is unsupervised, right? Whereas our approach is semi-supervised because we use a neural network to predict the categories. So that way it gets some information. It knows, for example, it knows how to ignore the background. If you were to use k-means directly, it's unsupervised. Maybe there is some background information there which is not necessary for your search, right? So the takeaway here is, cumulative gives better precision. I'm going to skip a few of the slides now. In fact, we compared with other popular vision APIs out there. I'm not going to mention the names. So the top 2, that's eBay. There are some caveats. This is really for products. When you're talking about commerce, like human-made objects, we are in the top. One of the reasons is the diversity of the data that we have, the image quality, right? Because if you were to take a picture of something, you're not going to get a white background image directly, right? So that's one of the reasons we are able to. One of the APIs actually has a human in the loop. That one is a little bit lower because humans are not very good when you're talking about 16,000 plus categories, which have so many different products, right? So things like, fashion, humans are pretty good at predicting the category. Hey, this is a dress, this is a shoe, and so on. But when you go to electronic items, right, measuring instruments and so on, they're not very clear where to assign. So that's why when you have human in the loop, it's not necessarily perfect. So just to recap, I talked about, I'll repeat a few times so you remember some things. I talked about the data, the diversity of the data. Stratified sampling is very important. When we train the neural network, we use neural network as much as possible to predict leaf categories, which is a little bit coarse, to predict aspects, which is a little bit finer, and also to extract the signatures, which is used for search. So all three, we use neural network. And when we extract the signature, we use binary. You don't necessarily need to have binary. We use binary. We extract binary signature using sigmoid. The reason to use sigmoid is so that we can threshold it very easily. And then I talked about remember the clusters with different colors. I mentioned that for search, given a cluster, you want more spread. If you reduce to a single point, you're not able to tell different kinds of shoes, for example. So that's one important thing. And also when it's good to narrow down your search as early as possible in the early stage, which is what we do, top K categories, and we look at only those buckets. And then we use binary embedding, binary signature to do the match. And also I mentioned use cumulative top K, not the absolute top K, because that improves the precision. Now, aspect prediction, this work by Hardy in our team. So these are some of the things that our system is able to do. For example, we have lots of examples of these kinds of faucets with different number of handles. So we're able to train the system to predict how many handles we have or what kind of denomination we have in the currency, right? Because people collect currency. And these are different things for fashion, what is a neckline? What is a pattern? Is it floral or is it striped? What is a brand, right? These are different aspects. So if you're looking at jewelry, what is the main stone? Because oftentimes color has information about the stone, right? And what kind of brand, even carrier because they have the logo on the mobile device. And product family and so on. One of the use cases is the following. When somebody takes a picture of an item, we can automatically predict these aspects and populate these fields instead of asking the user to fill. So that's one application. Here I show one of the sellers actually skipped style, material, season, and sleeve length, and we were able to predict those things to make the data more complete. I already talked about this, so I'm not going to talk about. Another trick I want to tell you is the following. So here, I'm not showing the y-axis because I don't want to show the absolute accuracy, but you see different colored curves. So each curve is one life cycle of our training. What I mean by that is the following. In this case, we used Café. We have a learning rate policy. Let's say we ran for 100 epochs, right? So each curve, each color is, let's say, 100 epochs. What we typically do is the following. We train till we get as much high accuracy as possible. That's the top of the gray curve. Gray is the bottommost curve there. And then what we do is we take the best model there, and then we change the learning rate. When you change the learning rate, it actually little bit higher learning rate, okay? Higher learning rate than at the end of the gray curve. So now the performance drops, of course, right? Because you're actually shaking the system. Now, when it converges, it actually converges at a higher value. And we keep repeating it, till you get all the juice out, right? So that's what we do. And you can see that there's actually significant improvement. You can actually get like 5% improvement between the gray and the red, roughly. So this is something I would encourage you to do, regardless of whether you train a neural network for computer vision or not, right? Once it converges, take the best model, feed it back with a different learning rate, higher learning rate, it will converge to a higher. Also, when we train the aspects, right, you may actually train this, let's say, brand prediction just from as a last layer, right? What we show here is there are specific aspects like brand. If you just use a last layer and add one extra layer to predict the brand, it's not good. That's FC only you see at the bottom, the blue. Because brand comes from different levels of information. It's a low level, mid level, high level information. Category is a high level information. So if you take a little bit lower levels, in this case ResNet 5 layer, you actually get better performance. But it's not true always, okay? So there are some aspects like sleeve length where the information is really at the high level. Okay, so in this case, you don't get a big difference whether you try to predict from the last layer or take it from a layer below, right? So this is something, encourage you to experiment with. And now, okay, first we talked about data, went through visual search, and then talked about aspect prediction, because aspect prediction will help you move more towards the fine-grained matching and also prediction. So now I'm going to take a deep dive into just the brand itself. You know, in this case, we looked at the network that was used to predict the brand, and then try to understand, dissect the neural network and see what it actually sees when you show an RGB image, right? Because we want AI to be explainable, right? If it's explainable, we'll be able to do more powerful things. So this is a recent paper at the workshop at ECCV. So if you want more details, I encourage you to take a look at that. This is what the problem is about. Okay, when I talk about brand, right, the thing that immediately comes to your mind is probably logo, right? In this case, this shoe doesn't have any logo from this angle. But people who know about this shoe will know that this Adidas NMD shoe, because of those things at the bottom, the two red, blue. It doesn't have to be red, blue, but those two blocks, the sole. And this one is an Air Jordan shoe. It doesn't have Air Jordan logo. It doesn't have the Nike logo. Of course, in this case, it has a print that says Nike, but it doesn't have the logo. What I'm trying to tell is, you know, brand is not always about logo, right? Here, this is a Nike Air Max. There is no Nike logo there, but people who know, they know this is Nike Air Max, right? This is a Puma shoe. Again, people who know about Puma shoes know this kind of, it has that curve and, you know, the sole shape and so on. They know it's a Puma shoe. But if you look at, so there are a lot of products like these, you know, as a human, you know, it's very hard for a single person to know all of these brands just by looking at the picture. But the machine is able to do that, right? So in this case, it's an example of narrow artificial intelligence, right? It's very good in excelling the human in a specific task, in this case, brand prediction, just from a picture, right? So our model, so this is what the neural network is doing. You feed an image, it predicts the brand. Now, I like this quote by Richard Feynman, which says, you know, I learned very early the difference between knowing the name of something and knowing something. So in this case, a neural network is predicting these Nike and Adidas and so on. But what does the neural network really understand? Why is it making these decisions, right? So that's what I'm going to show more here. So we used excitation backprop. It's one approach to actually take a deep dive into the neural network and see what kind of signal you get from different layers. You know, this is what we call activation map, right? So where are the neurons firing? Which regions of the image are they sensitive to? In this case, when it predicted Nike, red is high, okay? Red is high focus. The neural network is paying more attention to that part of the image. So, and you can see the red, the top red actually points to the Nike logo. So in this case, it actually understands a logo, right? So here, we didn't train Tigger to the neural network, right? We had lots of images with the label Disney. So it's, when it predicts Disney, it actually automatically learns the different Disney characters. So in this case, the heat map actually points at the Tigger region, right? Adidas. So even though there is Adidas logo, the neural network actually focused on the stripes from Adidas, right? So it's pretty interesting to see. This is Vera Bradley. Vera Bradley is all about these heavy patterns throughout that whole product. And you can see the red is kind of more distributed. It's more wide. At the Louis Vuitton, it's actually specifically looking at the monogram repetition and also this button for the clasp. This is the Apple. Again, we are talking about brands, right? Ignore there is some artifact when we ran it at that time. You see this red at the corner, 4 corners. There is some artifact. You can ignore that. You would actually see it in lots of images. But it actually learned to look at the home button, right? And here, you know, Apple is this beautiful packaging. It actually knows that one. And it goes beyond brand, right? For example, if you train a neural network to predict colors, in this case it's red color, you can see this red heat map is all over the image where you see the red color, right? And in this case, blue, it also hones on the blue color. In this case, it's not as well distributed because we are also trying to predict another aspect, which is hoodie. So it's kind of getting confused. Pattern. you can see this is a complicated image. It has multiple patterns, right? It also has a cow print, but it didn't focus on the cow print. It just shows where the stripes are. And the strongest stripes are highlighted in red. So I showed a few examples of brand, color, stripes, and you can go more, right? Style and so on. And these are the heat maps from the examples that I showed you. Remember, red is high activation, high signal. The neural networks are firing high. Blue means no signal, right? Like dark blue. So one thing I would like you to pay attention to a couple of things. The red intensity changes. Also, the extent of the red, how many pixels have the red color also changes across these images, right? So what we did was, we looked at these neural network heat maps using excitation backprop, and then we looked at two things. We looked at strength of the activation, these outputs from the neurons, and also we looked at how many pixels the neurons actually are getting the signal from. Is it very small? Is it from a small region or is it from a larger region, right? So, for example, okay, for this study, this is what we did. We looked at handbags. We looked at more than 1,200 brands with close to more than 3.8 million images. And then we trained the system to predict brand. And you can see these are the brands. Each row corresponds to a brand. These are the brand. So these are different example brands. Okay, some brands use heavy pictures, some brands use repeated logos, some brands use, like Burberry uses pattern, and the bottom one uses very heavy logo, the circular logo, right? So in this data set, 46% of the images had logo, right? And 51% didn't have a logo. But still, we were able to predict brand with a high confidence, okay? And 3% had repeated logo, because repeated logo is not very popular. Only specific brands use repeated logos, like Louis Vuitton, Coach, and so on. So remember, I talked about two dimensions, the strength and then the extent. Extent is how many pixels the neural network is sensitive to. So these are the brands where neurons fired with high strength. Right? So, and you can see almost all of these have strong presence of a logo. When there's a high strength, there's a strong presence of a logo, okay? And these are with high extent, okay? So in this case, you see like repeated patterns or repeated monograms, or sometimes large logo, right? So now, in fact, we see a whole spectrum of these. So when you plot in these two dimensions, extent and strength, different brands actually use different strategy when they are expressing themselves visually, right? So instead of looking at just logo, I would encourage you to look at some other signals like these to think about logo, logo detection. Brand detection, right? So if you remember, before deep learning, it was very popular to predict brand just from the logo using SIFT and whatnot, just geometric verification and so on. So this just shows that you can actually understand brand beyond logos, and there is a whole spectrum of it. If you think about it, logos are only in one corner, which is high strength, let's say, right? There's a whole spectrum. We also looked at neurons and understood, did an analysis to see, are there very specific neurons, or there are neurons that understand concepts in general, right? So in this case, Harley-Davidson, even though those images have different aspects of Harley-Davidson, there is a single neuron that actually just understands Harley-Davidson. And if you see Vera Bradley, Mary Frances, they both use patterns, but this neuron is just understanding these repeated, like heavy patterns in the object. The third one tries to understand, is learning like pictures, structured, non-repeating pictures in the image, and so on. The last one, I guess, it's looking at the shape. So there are neurons that are very specific, and there are neurons that are very general. So going back to visual search, right? We have these different bits. We could potentially actually identify these neurons, and then extract signature based on these neurons. So that is some investigation that we are doing right now. There are other applications. In this case, by understanding how when you show an RGB image, what does the network actually see? It's almost like an X-ray of the human body, right? It just sees these things when it sees brand or color and so on. Now we can understand specific neurons. By understanding these, we can also reduce unnecessary bias. We want to bias in the right way, not in the wrong way. So by understanding these neurons, we can actually change the weights of the neurons to reduce bias bad bias in the system. And also these neurons can be, understanding these neurons, you can actually do better personalization. Let's say, for me, maybe, let's say, Puma and Nike neurons are firing higher than Adidas, let's say, right? So in the personalization system, maybe we give special attention, higher weight to these neurons. By giving names to these neurons, we actually can understand and make the system better. So these are some applications. So I can do like a high-level overview of what we did, summary. We talked about data, diversity in the data. It's good to train the system with different image quality, stratified sampling, make sure that pictures are taken from different angles, different products, so that the network is learning richer representations. When it learns richer representation, you'll be able to do visual search better. Right? And then we looked at the simple hierarchy for visual search. We use neural network for everything, even the category prediction, aspect prediction, and also signature extraction. Signature extraction, oftentimes people use product quantization or K-means, which are unsupervised. Well, actually, ECCV, there was a paper, PQ, product quantization, which is supervised. But I encourage you to use as much supervision as possible. We use weak supervision to learn these binary embeddings, the binary signatures, using a sigmoid layer to predict the category. And now after we extract the information from sigmoid, we just threshold it to convert to binary. The reason we use binary is for speed also. And also, whenever you extract information, make sure you're actually using your bits effectively. So always encourage you to see, given the data, are you actually maximizing the buckets identified by these signatures, like these bits? Right? It's good to have some redundancy also, right? And then we talked about top K prediction. You want to quickly narrow down your search space, then search only within the top K categories. In our case, categories. For your application, maybe something else. And then top K, hard-coded top K is not good. You should make it dynamic by using cumulative probability to increase its precision. Then we dug a little bit deeper into aspect prediction. Showed some examples, like you can even do counting, right? Number of handles in the faucet, or material for jewelry. The color of the gem is correlated with the type of the gem. So I showed different kinds of aspects that we were able to predict, and also talked about how to train the network by feeding back again, right? Get your best model, change the learning rate, increase the learning rate. Now you will start with a low value, and then you end up with a higher value than where you started. And also these aspects, some aspects are at a very high level, like sleeve length. Some aspects, like brand, come from high level, mid level, low level, and so on. So depending on your aspects, you may want to train the model from the top layer or some intermediate layer. Then we wanted to see, what does the network see when you actually show an RGB image, so to make it more explainable. So we looked at brand prediction, and also showed that brand is not just about logo. It can actually come from different kinds of information. So we use 2 dimensions. One is the strength of the neuron. The other one is the extent of the neuron. What is the size of the region where it's getting signal from? Just by looking at these 2 dimensions, I showed a whole spectrum of ways the neural network is actually trying to understand, versus just looking for the logo, right? So by understanding these neurons, we also looked at the specific neuron, like specialist neurons and also generalist neurons. By understanding these, we can actually make our systems better, explainable, and so on. So hopefully you were able to take some of these takeaway messages and improve your systems. And I'm done with the talk and open for questions. Thanks.
Thank you, Robinson. We have some time for some questions. So let's We'll just do it out loud. So, first question.
Yeah.
So, my name is Suresh Sarkar. I work for HK Enterprise.
Okay.
The first question is for in order to extract the initial embedding.
Yeah.
What type of convolutional neural network?
So in the production, we have ResNet 50. Oh, repeat the question. What kind of neural networks do we use to train the category prediction and so on? So ResNet 50. So right now we are also experimenting evolutionary networks like AmoebaNet. They are giving very, very good performance because ResNet is pretty old. Yeah.
The second question is for your cumulative classification.
Yeah.
Were you using CNN all over again, or were you using something very?
So cumulative probability, are we using, are we retraining the system? Is it what you're talking?
To classify now, once you have found the category,
Yes.
what sort of inferencing are you using to derive the cumulative probability?
Oh, okay. The question is, what are we using to get the cumulative probabilities? Actually, the last layer is a softmax layer, which is actually predicting these probabilities, right? So those are relative probabilities. Like if you add them up, it should be 1. So we actually use that to pick the top K. So we don't use any new system. We use the existing neural network. Yeah. Yes. Yeah. Actually, when I talk about embedding is actually coming from a different layer. It's a lower layer, but the last layer is actually trying to predict the categories. So that's a softmax. So when we say top 5 categories, we actually take it from that layer. But when we extract the signature, like embedding for search, it's actually coming from a different layer, which is output from sigmoid layer, which not for category prediction. There's another not softmax, sigmoid. Yeah. Sometimes I confuse between sigmoid and softmax. Yeah.
Is it like one size fits all? Do you use the same network for all categories?
That's a very good question. In fact, in production, we use some fine-grained. There is 2 philosophies, right? So we are working towards a single model. So some of the benchmarks that we have, the one I showed here, in the production, we actually use PQ, product quantization, a little bit different. This actually performs better than the other one. So it's a single model. We use single model in production, yes. So for inferencing, what type of hardware we use GPU. For training the large models, we use TPU pod. TPU pod is very good. You can train in like a few days versus few months.
And for inferencing, you know?
Inference, we use GPUs. We use P100s right now. Not Hadoop. Hadoop is batch, right? No. We use a cluster of. Do we use a single node? We actually use a GPU cluster for inference. So when we get the input, we actually pool the requests. So and then batch them. And then do it. The response time is pretty fast. It's less than 100 milliseconds. We don't use H2O or anything like that, no. So right now, all the inference is done by GPU cluster. Yeah. Yes. Yes. What is the speed of similarity? So it depends. We have few systems. We also have system that is less than 25 milliseconds for the whole similarity thing, including. Oh, one given a query image, return top 1,000, it's about 25 milliseconds. And the inventory, it's about 500,000 for US. I mean, 500 million for US. Oh, pardon? So right now we actually use a cluster to do the ranking. It's actually like each node has a view of only portion of the data, and there is some redundancy across the nodes. So I don't know if I answered your question because I don't fully. Yeah, the data is divided into different buckets. It's centralized. It's one. Yeah, the ranking system is different from the inference system. Yeah, inference is CPU cluster. Inference is GPU cluster. Ranking is CPU cluster. Yes, the Hamming distance is CPU cluster. Okay, thank you so much. Any question? I'll stay here a little bit longer. So, thank you.